All right, welcome back everybody. So we're going to look at these three infinite series that are kind of a little bit less obvious than just kind of your normal geometric series. So for number one, we've got this addition and subtraction of terms. So what we're going to want to look at here maybe is the sequence of partial sums, right? So let's look at S sub n here. So, S sub 1 is just going to be 1. S sub 2 is 1 minus 1, which is 0. S sub 3 is going to be 1 minus 1 plus 1, which is going to be 1 again. S sub 4 is going to equal 0. And it's going to continue in this way so that our sequence S sub n is just going to look like 1, 0, 1, 0, 1, 0. And so we can see that if we add up the terms here, we're going to approach infinity, right? Because we're going to be 1 plus 0 plus 1 plus 0 plus 1. You're still adding 1 every other term. So the limit as n goes to infinity of S sub n, right, is going to equal infinity because you're just adding up the counting numbers for those odd terms. So because of that, right, clearly that's going to diverge, right? So that diverges. And we also know in particular that a sub n, where a sub n is equal to negative 1 to the n plus 1, diverges. So we know the sequence of terms diverges and the sequence of partial sums both diverge. So, that's going to be something interesting to think about in terms of if we look at the sequence alone, is that enough to determine convergence or divergence of the series? All right, so let's go ahead and look at number 2, the harmonic series. So we're adding up 1 plus a half plus a third plus a fourth plus a fifth. Now this is a famous series, and there are hundreds of probably different proofs of this series. So what I'm going to do is I'm just going to present one particular one that is going to use a little bit of an inequality argument, but you can find a lot more online. So let's suppose that this is equal to S. Right? Let's suppose that this series has some sum. We'll call it S. You could use lowercase like the definition or uppercase. I'm going to use uppercase. So we'll note that the sum is equal to 1 plus a half plus a third plus a fourth plus all of those terms. And then what we're going to do is we're going to make an argument using inequalities. So I'm going to shrink this series down a little bit. So this is going to be less than 1 plus a half. And then what I'm going to do is I'm just going to take the even reciprocal powers and duplicate them. So I'm going to have 1/4 plus 1/4. So note this is instead of the 1/3. And 1/4 is smaller than 1/3. So if I do this continually, so we'll have 1/6 plus 1/6. So now I'm replacing 1/5 with 1/6. And then 1/7 with 1/8. And we're going to continue to do this for all terms. So clearly the series on the right is going to be smaller than our original series. So this is just going to be by construction. Okay. So then let's do a little bit of work here then. So we're going to go to our series here and we're going to group terms. So we're going to group them this way. And we'll see if we notice something about that. So we've got 1 plus a half, and then 1/4 plus 1/4 is 2/4. 1/6 plus 1/6. Maybe we'll just use the same color throughout here. Is 2/6, which is 1/3, and then 1/4. So note. So that's going to continue on, which means I'm going to have 1/2 plus 1/3 plus 1/4 plus 1/5. And so we've really kind of reconstructed our series here. So I've got this 1, and then if I add it to all of those guys, I get my original sum. So let's just note, I'm going to rearrange a little bit. So I'm going to move that 1/2 in the second spot. So we're going to swap those first two terms. But then, no, actually we can just put equal signs here since we're not removing terms here. So no, these are all equal to this smaller series above. But then that means that this is equal to 1/2 plus s, right? That's our original series that we had. So note what we've come up with. S is equal to 1/2 plus s. But this is a contradiction. Thus, the series diverges. Now this is big because it's completely not obvious that this should diverge. And moreover, this sum goes to infinity, which is pretty crazy because you're adding these reciprocal values. So the values are getting smaller, yet this is still going to diverge to infinity. It takes a very, very long time, right? N is going to have to be much, much bigger to really show that kind of growth. It's going to grow incredibly slowly, but it will approach infinity if you have enough terms. And another note is that, let's just note that our sequence goes to 0. Right, so our sequence is approaching 0. So if we took the limit of the sequence, right, that's obviously going to go to 0. So the limit of the sequence goes to 0, but the series itself goes to infinity. So that is a very different conclusion than what we got with the first example above. And that's going to be important. All right, so the last one, if you've looked at it a little bit, we'll see that this is a geometric series, actually. So if we take some common ratios and divide the term in front by the term previous, we'll see that we'll get negative pi over 4, I believe it is. Yeah, so it's going to be negative pi over 4. So we're multiplying by negative pi over 4. So now a sub 1 is pi over 2. And note pi is, a little bit bigger than 3. So this is going to clearly be less than 1, which means we're good. So the sum is going to equal pi over 2 over 1 plus pi over 4, since it's negative. And so we'll have pi over 2 over 4 plus pi over 4, which is going to become 2 pi over 4 plus pi by reciprocation. So that one's going to be pretty easy to calculate. But these first two are just some slightly different types of series. Harmonic series is going to be a super important one. This is going to be one that you want to kind of file away in your brain because it's going to show up quite a bit. All right, let's look at some other ones. So we've got the sum of n equals 1 to infinity of 2 to the 2n times 3 to the 1 minus n. So the question is, like, how do we interpret this one? So we can see that we're multiplying geometrically, it looks like. So what we're going to want to do is play around with our expression a little bit. So let's actually do this off to the side. So note we could write this as 2 squared to the n times, we're going to have 3 to the 1 times 3 to the negative n. So that means this is going to look like 3 times 2 squared is 4 to the n, and then 3 to the negative n is just 1 over 3 to the n. So we could rewrite this as 4 over 3 to the n. So clearly, r is greater than 1, thus diverges. So that's going to be a divergent series, but this rewriting of exponential terms is going to be very common. Number 5 is much more interesting because, like our harmonic series, we're just taking reciprocals, but now we're taking the reciprocal of the counting numbers and then the next number multiplied together. So we got a product here. So this one is also kind of a famous series. And the way that we're going to approach this actually is by partial fractions. So if I have a over n plus b over n plus 1, then we can maybe kind of split this up into 2 pieces and work with those 2 pieces separately. Because if I have a product in my sum, that's a little trickier than to work with a summation in my sum. So note, if we go ahead and try to solve this, this is going to be equal to 1 since that's our numerator. What we'll get is that an plus a plus bn is equal to 1. So a is equal to 1 and b is going to equal -1. So again, I'll let you verify that, but that should be pretty obvious. A is going to be, because a plus b is equal to 1. Oh, sorry, a plus b is equal to 0 since there are no n's. So a is 1, b is -1, which means we can rewrite this as the sum n equals 1 to infinity of 1 over n minus 1 over n plus 1. And maybe, you know, here we would want to split, but note we can only split this into 2 separate series if each one of them converge. And we know that this is the harmonic series and does not converge. So we cannot split this series. But we can kind of write it out and see if we can figure out what this is going to look like in its expanded form. So if I write this out, I start writing out terms of this series. So we'll have 1 minus 1/2. So note that's our first term. And then we'll have 1/2 minus 1/3, and then 1/3 minus 1/4. And that's going to go all the way until you get to kind of the end of the series. You can kind of think of it as of 1 over, so we'll have 1 over n minus 1 over n plus 1. And note, this series doesn't really end, but we're actually going to get kind of the same behavior throughout, which is that all of these terms are going to cancel. All of these previous terms are going to cancel. And that's going to continue on for any value of n. So again, we're going to think of this kind of as a finite series first. So this is the sequence of partial sums. Right, so if we took the sequence of partial sums, we're going to get that this is equal to 1 minus 1 over n plus 1 in general. So that's going to be s sub n. But then if I take the limit of my sequence of partial sums, clearly that's just going to equal 1, since 1 over n plus 1 goes to 0 as n goes to infinity. And that limit of the sequence of partial sums is going to be the sum of our series. So that's going to equal So we do want to be slightly careful here that the object that we are considering here when we write it out is a partial sum, right? Is a generalized partial sum, not the infinite series itself, because the infinite series continues on forever. So that's why that sequence of partial sums convergence is so crucial to proving convergence of the infinite series. All right. So the last one is going to be a crucially important one, actually, that's going to take up most of our chapter when we get to power series. And so we get this expression 1 plus x squared plus x cubed plus x to the fourth, where x is bounded between -1 and 1. So clearly this is a geometric series. And this geometric series is going to obviously have a sum, which is going to be 1 over 1 minus x, right? Our common ratio. So r is equal to x, and a sub 1 is 1. But we should note something here that is pretty spectacular. So on the left, we have this infinite polynomial, right? So x is some variable between -1 and 1. And on the right, we've got a rational function. So what we're saying here is that this rational function can be approximated by a polynomial, right? Now, the infinite polynomial is equal, but suppose I cut this off at certain chunks. So if I only have 4 terms or 5 terms or 6 terms, that's obviously not my full infinite polynomial, so it's only going to be an approximation. So note that your sequence of partial sums, your S sub n, is going to be approximately 1 over 1 minus x. Whereas the actual sum itself is going to be your infinite polynomial. But if I take partial sums, that's going to be approximately our function, which means that we're also going to have to be introduced to some type of error as well. So, right, so S sub n minus 1 over 1 minus x is going to equal the error, the absolute value, let's say, the error in approximation. Right, so if we consider it at a particular value, it's going to be the error in approximation. And maybe we put x sub n here. Or no, I guess not. We could leave that off. And so this is going to get to our, what we talk about with approximations is what we're going to use this geometric power series. So note, this is called a power series, simply because it's made up of powers of x. And this power series is going to be used to approximate this other function. And that's going to be a really, really important idea for us. Okay, and then we'll add a comparison test here as well, which is if we let a sub n and b sub n be two sequences where a sub n and b sub n are greater than 0 for all n. So these are non-negative series, non-alternating series. If b sub n converges and the terms of a sub n are less than or equal to b sub n, so each term by term comparison is going to be smaller for the same value of n in the series, then a sub n also converges. So you can think of this as like a bounding test. So we're bounding it above by this convergent series b sub n. Our terms are always positive, so we're not going to drop down to negative infinity. And so because we can bound it from above, that is going to prove convergence of our smaller series, or series of smaller terms. All right, and then the opposite is going to apply. So if b sub n is a divergent series, and a sub n is not bounded by b sub n, so a sub n is greater than a b sub n for any n in the series, then a sub n is also going to be unbounded and diverge. So note this is kind of like an unbounded test. And this is going to be really important for evaluating specific series where it's going to be easy to find a convergent series or easy to find a divergent series, and then use this inequality argument to show that the series that we're looking at in our particular problem is either bounded by a convergent series or unbounded by a divergent series. All right, so the quick note about 6 is kind of what I mentioned already, that this infinite polynomial equals the rational function. So it's kind of the same idea here. I've just put it all up at the top. But it's the idea that we can use this infinite polynomial expression, which is a geometric series, to approximate this rational function. And then by making that connection, we're also going to apply calculus to these series. So that means that for our quick note, let's say 1 plus x squared plus x cubed. So if we note that these are equal to each other for x, absolute value of x less than 1, then that means that the integral of these objects are also going to be equivalent as long as x is bounded between -1 and 1. Which means that we'll get x plus 1/2 x squared plus 1/3 x cubed plus 1/4 x to the 4th is equal to, well, what's the integral of 1 over 1 minus x? Well, that's going to be the natural log of 1 minus x with a negative sign, I guess. Right? And note, maybe there's a plus c here. We haven't really kind of discussed what's going on with these particular series and this type of integration technique with it. So what we would get is, negative x minus 1/2 x squared, minus 1/3 x cubed minus, right? All of those things are equivalent to the natural log of 1 minus x. So now we've got a method for finding these objects together and then using integration to create a new infinite polynomial approximating some function, in this case a log function. So the question is, does derivatives also work for this? And it turns out yes, we can also differentiate both sides of the function. And the differentiation will still carry over convergence on this interval. And so this interval is going to become very interesting to us because we want to know what it is. And this is the interval of convergence. So again, there's going to be lots of ideas that we discuss related to this comparison of an infinite polynomial, which is really a power series. It's a sum of the terms of a sequence, equaling some function of x that we're familiar with. So there's going to be natural log functions, rational functions, trig functions, exponential functions, as well as inverse trig and things like that as well. So if we look at all of these convergent series, so these are ones that we worked on previously, what is true about the convergence of each of the sequences associated with these series? So this is pretty obvious that if we take any of these sequences, a sub n's down here in the bottom, right? All of these sequences converge to 0. Right, so this goes to 0, this goes to 0, this goes to 0, this goes to 0, as n goes to infinity, of course. So the question is this always true? Right. So is it always true that the sequences of our series, not the partial sums, but the sequences themselves that we're adding the terms of, will converge to 0? And the answer is yes. If the series converges, then a sub n goes to 0. Or a sub n converges to 0. And note, our series is converging to L or S, whatever you want to call that summation. So that can be any number. But the sequence itself will converge to 0. However, if a sub n goes to 0, as n goes to infinity, does the series converge? And the answer to that we've already seen, which is no. Right, and this can be, so the proof of this would be the harmonic series. So this is a one-way proof, a one-way statement, right? So if the series converges, the sequence converges to 0. And that's going to be really, really important, because what that means is that if we're evaluating a series, the first thing we can look for is the convergence of the sequence, right? So that's where we get this divergence test for series. So because this is true for all convergent series, a sub n converges to 0. And no, we haven't proved this yet, and I might provide a proof in a separate video. What we can say that is if a sub n converges to any non-zero number, or diverges, then our series diverges. So we can look at the sequence first and say, what's our sequence doing? Because if our series converges, we know that the sequence itself has to converge to 0. So this is going to be another test that we kind of start with some obvious series where we know that we're going to get a non-zero number for the limit as n approaches infinity of that sequence. All right, so this is going to conclude our notes for today. If you have questions, definitely come by my office hours or shoot me an email. And we're going to be continuing with series throughout this chapter, jumping from the book that we're in, the James Stewart book, to the supplemental book that I'll be using, which is the Domano Waits Kennedy calculus book. So until I see you next